Well, I want to do a couple more of these shared moment equations for you or with you. And here's one where we have a uniform or have a triangle load, an increasing load. And I'm giving you some values here. I'm saying that the height up here is equal to 50 pounds per foot. And each half length here is equal to 10. Given those things, I should be able to solve for the reactions over here. So the reaction here is AY. And there should be a moment about A. And over here, you can see how I've solved for those. And so I have a moment about A of 6667 and a force at AY is equal to 500. All right, so if I want to find out the equations, I draw a little section, draw a free body diagram. I have positive A, positive moment about A or at A. This is the reaction. Positive shear, positive moment, distance x. The triangle load has to stay there. So here it's kind of helpful to know what that height is so I can evaluate the triangle load. So going back to our little formula that we developed a little bit ago, it's a ratio of the distance in x over the total length times the height. So in this case, it's x over 20. The original height is 50, so I get y is equal to 2.5x. In other words, this is increasing at 2.5x as it goes forward. The resultant then is equal to 1/2 BH. So 1/2 x and the height here, or the y is 2.5x, so that gets 1.25x squared. The resultant x, because it's a triangle load at 2/3 x, so all we have to do then is just sum the forces in the y to find the shear equation. Let me move that up a little bit. I guess I can get the whole thing in. Sum the forces in the y. I got 500, which is that. Got resultant negative of 1.25x squared minus shear, and I get an equation for the shear. Sum of the moments about A. I have that positive moment minus the resultant times 2/3 x going in that direction minus the shear times x going in that direction plus the moment as a function of x. And I'll let you follow my math. You can kind of look and see how I did, but I get a moment function with an x and an x cubed and a constant. Well, another way of discovering the moment equation is to integrate the shear equation. So from our prior work here, we have our shear equation. And from our textbook, we have this little graphic. It says that the change in moment is equal to the integral of shear as a function of x dx. So let's go ahead and do that. I have my shear equation, and I can say that moment is equal to the integral of shear dx, integral of 500 minus 1.25x squared dx. Integrating, I got the moment is equal to 500x minus 1.25x cubed over 3 plus a constant of integration. Now, how do I evaluate the constant of integration? Well, I do know that in all cases, sum of the moments is equal to 0. And over here, I have something that's going on. This is the point at which x equals 0. So let's go ahead and write our moment equation here and see what we got. I'll say that at x equals 0, moment is equal to the constant. I also know that, let's draw just a little section here. I'm going to say that this is tiny section where x is equal to 0, and this is what it looks like. I have a moment at A, and I have the moment as a function of x. Knowing that the sum of the moments is always equal to 0, I could say that MA plus moment is equal to 0 at x equals 0. So that says that the moment as a function of x is equal to minus MA. From our previous page, the moment at A is equal to positive 6,667. So that says that m is equal to negative 6667. And that's going to be equal to the constant of integration. So I shortcutted it here just a little bit. I just wanted to give you that little bit of an explanation. Finding that constant of integration, I can put it into the moment equation, and there we have it. And again, that agrees with the prior page. All right, this is a homework problem that I want you to work on, but I just want to help you set this up, write the equations for this. And what you have to do is recognize that there are two, there's the triangle load and a rectangle load. So let's just go ahead and draw that in there. I'll let you figure out the resultant, or the AY and BY. We know that there are going to be some reactions there. But if we want to find things as a function of x, we draw a little section and draw a free body diagram. So in this case, I have a uniform load on top of a triangle load, where this is all right there. You'll find AY and shear and moment. What you'll have to do is say that there's going to be a resultant of the uniform load as a function of x, and there's also a resultant of the triangle load as a function of x. This will be acting at x over 2, and this one is acting at 2/3 x, if you can read my, my writing in there. This is going to be 200, which you've already got, and this one will have some y is equal to x over L times h value that you need to kind of figure out. Anyway, once you do that, you just follow those steps as we just did before. Sum of the forces in the y to get the shear, and sum of the moments about some point to get the moment equation. All right, and what I want to encourage you to do is do these fundamental problems. These are quite easy, but this will give you some good practice. These are all in the back of your textbook. Do them all. I'm not going to assign them as homework and make you turn them in or anything like that. Just work on them. This would be very good practice for you.